Good morning, ladies and gentlemen. Glad to see you. Glad to feel you. Today is the last lecture of our course, and I will change the topic again. We will talk today about relativistic quantum mechanics. Right. It doesn't have to be a part of this course. We are talking about earth things, mostly condensed matter, which kind of rather close to everyday practice. As to relativistic quantum mechanics, well, perhaps it is not that practical, although there are exceptions from this. But, well, relativistic quantum mechanics is about inner intimate structure of our world, about the fact that our world is in fact Lorentz invariant. That's the most important thing. And we will talk about Lorentz invariance. We will talk about that strange property of our world, which we cannot see every day. And talking about this, we will first outline most important concepts of relativistic mechanics. Then the question is how to write an analog of Schrödinger equation for this for relativistic particles. They will be tried, but eventually it doesn't fit for, at least for electrons, for fermions. And we will spend some time studying dirac construction, trying to understand how does it come about and what does it mean for our world. Right, that will ultimately allow us to deal with relativistic quantum mechanics to describe physical vacuum in very much the same terms we have described any system which came in our course of advanced quantum mechanics. There is a vacuum, there are excited states on the top of it, there is interaction which can lead to interesting consequences. And for us, for today, there will be electrons, positrons, and photons in the game. I don't want to go further. I just want to bring you to the beginning of the road, following which one can actually achieve full understanding of relativistic quantum mechanics. I should say that mathematical apparatus, which is commonly used in relativistic quantum mechanics, is a bit different. Although the substance is, of course, the same, but because of Lorentz invariance, they prefer to use Lagrangians rather than Hamiltonians. I certainly in favor of Hamiltonians because it is most closely related to quantum mechanics, to general quantum mechanics. That's why we'll stay with Hamiltonians during this lecture. Good. Let us go on with the stuff. I will be talking about Lorentz invariance, but the name which comes first is not the name of Lorentz. It's the name of German mathematician Minkowski. So it's one of the highest honors in science, where all the space we live in is named after you. We actually live in Minkowski space. He was, as I said, a mathematician, and most part of his life he's been doing rather abstract mathematical problems. Then at some stage, somebody told him that physicists also have mathematical problems. From time to time, he began to attend seminars in physics. He learned interesting things, which kind of energized his creativity. And he came up with this idea, and he completely understood how great it was. He wrote about great discovery, which brings together space and time in one entity in four-dimensional space. Shortly after this discovery, he passed away unexpectedly, so nobody knows what would happen in science if he stayed longer. Anyway, it's not about personality, it's about Minkowski space. So what kind of space is this? It is a space, four-dimensional space, which is made from points. And one point in the space is called event. It has 3 space coordinates and time coordinate. Let's take 2 points like this. And let's make the following combination out of the coordinates of the spaces. Right, that looks like a distance. This is geometrical distance between the points in space. And this time difference. And Minkowski said that altogether, this forms an invariant independent on coordinate system, whatever if it moves or not. Right, if you're talking about non-coordinate systems which do not move, well, it is kind of obvious. It's just about geometric distance. So one can measure the distance between 2 points A and B in this system of coordinates, or one can take another one. One ends up with the same distance. But if the systems move, that doesn't hold anymore. Geometric distance can change. And also time interval can change. And only taken together, they form an invariant, which does not depend on the coordinate system. Right, that's a property he has figured out. The development of physics, which preceded that, was understanding electromagnetism. And he was brave enough that saying that it's not about electromagnetic waves, it is about our space, the world we live in. Good. What I wanted to add here, there are different ways to make this expression more symmetric. And at this lecture, we will use a little bit old-fashioned way. Then the fourth coordinate is purely imaginary. So we define x4, which is imaginary unit times ct. Right. With this, we conveniently have for distance all the sum of all four, but be careful, right? If x for the real, it would mean that the invariant is always positive, but it's a kind of most interesting property of our space that this invariant doesn't have to be positive. It can be positive as well as negative. All right, so we talk about Lorentz invariance. You certainly have heard about this, perhaps in your first year, when you've been talking about physics in general. That's where it comes once again. Sir, any questions about this most important item in physics? Don't think I can see chat. No, chat. I can see chat. The chat is empty. Fine. If there are no questions, let me assume that you have swallowed it. And let's look at consequences. It is kind of elegant and beautiful that the consequences are very instructive and rather unexpected, just elegant. Let us look at the consequences. First of all, let me talk about a Lorentz transformation. So what is this? Is a transformation of this vector characterizing an event, transformation of a vector, from one reference system to another. Its linear transformation can be written in matrix form. So there's 4-vector matrix 4 by 4, which transforms it into a different vector. An example of this transformation is just a rotation in 3-dimensional space, but it's not so interesting. All right, what are the properties of this matrix? Let's see, that has to be constant. The only way to achieve is to impose this property on matrix lambda. It's written in indices. How can we rewrite it in terms of matrix multiplication? Oh, come on, we will be dealing with matrices for most of our lives, so let's figure out this. Take a second look at the expression. So those are external matrix indices, mu and gamma, and this is internal one. And okay, the notation which I introduced is a summation over repeated indices. Very convenient notation in relativistic theory. Good, so it looks almost like a matrix multiplication, where matrices are usually coupled with first and last index. So eventually I have to invert indices here. And with this, I can write it as lambda transposed times lambda equals to a unity matrix. Right. So rotation in three-dimensional space is one of the examples of such matrix. More interesting example is a transformation to a reference system which moves a certain constant velocity. Let's measure this velocity in fractions of speed of light. Right, and let us assume that it moves in direction x3. So for x1 and x2, we just have a diagonal block in this matrix. And it's non-diagonal. It mixes x3 and x4, one of the coordinates and time. And look how tricky it is. Right. What we can see, it's a denominator which blows up if beta approaches 1, if velocity approaches velocity of light. This is light barrier. One cannot really jump over the singularity of this matrix. One cannot move faster than speed of light in our space. All right, and otherwise there's a mixture, there's non-diagonal element which mixes time and space. Let us see, let me make some practical example. Okay, since relativistic events rather far from our everyday experience, let me take experience from TV shows. Let me turn to Star Trek, and let me consider a cosmic ship, bird of prey. Here's my favorite control question. Well, I will ask them in a minute. Just be prepared for a question. Good experiment. If you look at bird of prey and it doesn't move, it has a certain length. However, if we look at moving bird of prey and make, for instance, a snapshot of it, we will see certain distortion of its shape, and in fact, the length at which we will see it will be smaller than original lens. I should say original value. Yeah, that's very strange. I mean, why does it depend on coordinate system? But anyway, there is experimental fact, although structured by their scenarios is not relativistic universe. Let's assume that relativistic laws are valid over there. Good. So let us try to compute what is the apparent size reduction. Sure, how we should proceed. We have this Lorentz transformation matrix. I need a little bit more space. No, I guess I can manage here, which I can write as 1 minus p squared is it so? I better check. Yeah, this minus here. Here must be plus, here minus. Doesn't matter much. It is the direction of velocity. Good. So let's try to compute it. It's one vector to be transformed in other vector. And what do I have in the system of um, at rest? Well, what do I have? I have original L. No time interval. So now I'm ready to transform. The answer has to have L prime over here. Let us see if I transform, multiply it. I got 1 over square root 1 minus beta squared. Oops. It looks our calculation doesn't correspond to experiment. This is bigger than 1. So our formula predicts that the length of the bird of prey, if it moves, is much bigger than original length. So, ladies and gentlemen, who knows what went wrong? Let me formulate it differently. Who does not know what went wrong? I can want to have some contact with you. Right. Okay. Good. They don't know. I made here an assumption, which is very much based on my practical experience, and which is natural but erroneous. Namely, I assume that the vector which I should transform has no time difference. It means that when I'm making my snapshot, I assume that light which comes from cockpit and from after part were emitted. The light was emitted simultaneously in the coordinate system of bird of prey. But this is not good assumption. In fact, good assumption that I take that photons in my coordinate system simultaneously. So one has to write a little bit complex equation. One has to put 0 here. And here, there's some unknown delta t. What does it mean? What does it illustrate? It illustrates a very important message from relativistic quantum mechanics, which is completely counterintuitive for us. Events which are simultaneous in one coordinate system are not simultaneous in moving coordinate system, right? So here events of photon absorption were came in same time for us, but in the system of coordinate of bird of prey, they've been emitted with sometimes time difference. Good. Then what do we need in order to compute the reduction? Well, basically one has to solve these equations with respect to unknown delta t. And then it all comes good. It will be that L prime is reduced with respect to L. Good. Events which are simultaneous in one coordinate system are not simultaneous in another system. I hope you got it with this illustration. Oh, I promised control question. As a control question, what is the length of bird of prey? That might be a little bit unexpected question, but well, you're a physicist, at least in near future, and physicists got unexpected questions from well, very frequently, and they have to answer. So please train. I'm waiting for a reasonable estimation of the length of this ship, bird of prey. If somebody read the book, it's given, okay? And the exam will be such that you will be able to use books. We could not forbid it. Right. I don't think it helps much, frankly, but well, you can always try. So please, somebody who is not sleeping yet, who is physically present, just give me, please, estimation of the length of this cosmic ship. 109 meters. Yes. Okay, that's something reasonable. That's what one can kind of estimate, like 10 to the 2 meter. 1 kilometer is probably too much for a cosmic ship. 10 meters, well, it doesn't look very impressive. So something between 100 meter. Eventually, I don't know what Google says. Eventually, it's 95 meters. But thank you, Pepin. It's good estimation. Fine. Let's go further. Oh, there's something bad with my screen. Oh, no, it went further. All right. So let me see what happens with the concepts of classical mechanics in relativistic world, and how we can use symmetry in order to establish new physical laws. Right. Let's talk about let's assume, and yeah, this is natural assumption. One can actually prove this very mathematically. Let's assume that all physical quantities are transformed with Lorentz transformations in a certain way. just mathematical. Okay, assumed. It means that there are no three-dimensional vectors in our space because Lorentz transform only knows four vectors, right? And that's one of the possibility. Physical quantity can be a vector, a four-dimensional vector, which means that upon Lorentz transforms, it is transformed like this. There can be scalars. As usual, we know them of scalars in that word. That has to be invariant with respect to Lorentz transform. How to achieve invariance? Simplest way is to arrange an inner product. Like inner product of two vectors is a scalar. The same should be valid for four-dimensional vectors. So we write this inner product summation over the indices, right? This expression for inner product is based on the fact that x4 is imaginary. It won't work otherwise, but this is assumption for this lecture. Good. One could also think of tensors, quantities, which will have, okay, tensor, which would have two indices. And there will be some transformation law, which would involve, for instance, two, how shall I write it? I believe which would involve two Lorentz matrices. But we don't talk about tensors. Later, we will talk about spinors. But well, let's wait for this. Good. So symmetry suggests that all physical quantities are scalars or four vectors. Very good. Let us apply it. Let us consider a vector of momentum. It is a three-dimensional vector. It needs to have a counterpart. And by applying Lorentz transform, we immediately see that the counterpart, yeah, I should not say have said counterpart, just a part, a lost part, for fourth dimension. This fourth dimension must be energy, right? So momentum and energy of a particle, they form a vector which has three dimensions of spatial coordinates and dimension of time. And this is energy. Well, divided by speed of light. Of course, all components of the vector should have the same dimensionality. All right. So that's kind of what is a discovery which is commonly ascribed to Einstein. If you compute now the energy of a particle at rest, what do you get? Why don't you substitute it in this formula and give me the answer if you don't remember? Yes, perfect. Thank you. MC squared. Energy of a particle and rest, Einstein formula. Let's go on. Let's try to apply the same property to other vectors. Vector of gradients. Differentiation with respect to coordinates must be supplemented with a fourth coordinate. Differentiation with respect to all right. Let us now try to make a scalar of the gradient. We take inner product of two gradient vectors and see what we have. That comes with, this is gradient squared, second derivative, and that is time derivative with minus sign. It's important. So it's called the Lambertian operator, has a special sign, squared. Squared, perhaps to remind you about 4 dimensions. Right. And one can make a wave equation taking Hamiltonian to work on some function. Let's make it scalar function. You can get Maxwell equation in some gauge if one applies it to three-dimensional vector potential. But wait a second, vector potential is a vector. Vector potential is a vector, so it needs a scalar counterpart to form four-dimensional vector together. And that is the other potential. So only in relativistic mechanics, these two potentials finally become brothers, finally become components of the same object, four-dimensional vector potential, which has a spatial part and time component, which is a scalar potential, which is what we call in non-relativistic science scalar, just the potential of electric field, electromagnetic field. Good. So with this, we finally see the link between the two. Right. Let's talk about fields and currents. Current density. Current density is also a vector. One has to find coordinate counterpart, and right, yeah, for me it is still kind of sounds funny, although I kind of learned it 50 years ago. Still sounds funny. The current is related to density. If one changes coordinate systems, part of the current becomes density of particles. Marvelous. Current conservation. Well, usually you write it like this. Divergence of current, all zero, not very symmetric. In relativistic quantum mechanics, if one assumes this, it just becomes a piece of cake. It's four-dimensional divergence, which is zero. Very easy to remember. Right, Maxwell equations. Now it's in four-dimensional form and with a source. That's Lorentz invariant form of Maxwell equation. Here we have scalar, the Lambertian. Here we have for vector, and we have for vector of electric current. And this is, you know, that strange constant which comes from System International. I don't know why does it stand here. I'm not responsible. Good. So we eventually combine the quantities we know from non-relativistic quantum mechanics and see that eventually they are very much related in relativistic world. So I guess I have all relations which I needed. And let me try to get to quantum mechanics. Let me try to write something similar to Schrödinger equation, but that possesses Lorentz invariance. It's interesting to know that it was eventually initial problem formulation of Erwin Schrödinger. Lorentz invariance was pretty much known. By the time he decided to derive his equation, quantum mechanical equation. So he wanted to make it Lorentz invariant. But soon he understood that there are problems which he could not overcome. So he decided to write it for non-relativistic case. And he was very right. He was very right to do this, although it looked like step back by that time. Schrödinger equation is, if you ask me, is more fundamental than the equation which we'll attempt to write now. Well, equation for which is called klein-gordon equation. It is based on a simple hypothesis, and hypothesis is as follows. We need some equation for a wave function which involves coordinate derivatives and time derivatives as well. And if we really would like to obey Lorentz invariance, we need to write a scalar here. And the only scalar which we have, which contains its derivatives, is the Lambertian. So it becomes a wave equation, right? We write it for a particle with a mass, in distinction from massless photons. So that has to be here. Good. That looks like a very good equation. It reproduces what we know of energy spectrum of particles, right? So let us see if one takes plane wave. Well, and so what I have here is wave vector energy, right? One gets the spectrum, which is relativistic. The problem which appears here is that this energy spectrum, which we derive from this equation, can be positive as well as negative. So if I sketch, for instance, energy versus momentum, just asymptotics, and I want to sketch the spectrum. It has a positive branch, as you all know, and that corresponds to energy of a relativistic particle. But it also have negative energies. And if I would try to arrange, okay, negative energies look strange, but eventually in some means we understand that negative energies have to be here anyhow. More important obstacle by applying klein-gordon equation is that the solutions with negative energies also have negative probability density. And it makes strictly no sense because, yeah, wave function has to be related to probabilities, negative probabilities. Do not make sense. So there were problems people have encountered at some stage, so they didn't know how to write relativistic string equation. If you look at it, just from purely practical, pragmatic point of view, it's no problem. I can solve it in a second. What I want to write is a usual string equation. Let's see. And I just put into Hamiltonian a known expression for energy. Let's see. I would just put square root of basically I'm rewriting this expression. That would make an equation with only a positive branch of spectrum, just by definition. So any ideas why people did not go for this? Why people don't accept this equation as description of reality? Okay, we are nearing break, so I would like to round up this transparency. So let me just stress rather strange idea. People have rejected this equation in first first because it's not elegant. What is elegant are local derivatives. So the derivative of psi in given point of space will depend only on local properties of psi in this space, only from derivatives. Yeah, for instance, first derivative, second derivative, it's all fine. But if one writes this equation in X representation, one would try find a form of this side, of this kind, integral kernel. It will break non-locality. And if one looks at it attentively, it will also break the mere notion of relativity, because it means that it will depend, the derivative over here will depend on psi at the same instance, which is not good. Right? So this klein-gordon equation is not good to be a replacement of Schrödinger equation for in relativistic mechanics. So this is me again. Let us start the second half of the lecture. We've been looking at klein-gordon equation, trying to make this equation a replacement for Schrödinger equation. It didn't quite work. We need a better idea, or whatever, they needed a better idea. And the idea was related mathematically with square roots of the Lambertian. Why was it so? Well, just because the equation had too many roots. So it was an idea to separate the operator in this equation into two parts. Right? Like this. And you can do this if you take this equation as fundamental equation and forget about this one. Right? It's a bit like you've been doing at school, solving equation x squared equals 1 1 or whatever x minus 1 is 0. It has two roots plus minus 1. Let us rewrite it in this form. And let us concentrate on the solution plus 1. So we need to neglect this term. Right? So the initial impetus was like this. Let us look at square roots of the Lambertian, because we can solve the problem with those to get rid of the solutions which we don't like. Right. So there's an introduction of square root of the Lambertian. There are many ways to extract square root from the Lambertian. What are the criteria one can introduce in this respect? First of all, this procedure has to be Lorentz invariant. And second, it has to have some elegance. Good. That's how Dirac came to the business. He just happened to have, because he was a very young person, he didn't think much of the consequences of the ideas he put forward. And he was also very well mathematically educated by that time. So he knew how to deal with matrices and with math. And he quickly understand that if one looks for the square root in this form, where these are gradients, and one has to have gradients, one has to square it to get second derivatives which are in the Lambertian. So one can look at it as a gradient and some matrices. The matrices which are not yet known, but if we substitute this expression, we need to get Lambertian, and there is important constraint on this matrices. Look, this relation is not that different from anti-commutation relation on creation and annihilation operators of fermions. It's the matrices anti-commute unless they have the same indices. But anyway, it's not, by no means those are creation and annihilation operators of electrons, just mathematical analogy. It's important, it can be derived substituted into the equation. You can do this. The problem that one can eventually satisfy this relation with many matrices, so there is still plenty of choice. What was, that's where mathematical education and talent of Dirac went. He knew that the minimum representation of these matrices are 4x4 matrices. One can take a set of 4x4 matrices which satisfies this property. One cannot do it for 2x2 matrices, for instance. Good. So this is, that was his construction. So let's look for square root of the Lambertian in this form. Then let me perhaps rewrite the equation coming back to this transparency. In this way, the equation will become right. So that brings us to Dirac equation with a concrete choice of gamma matrices. This is a little bit abstract notations. Here we have this anti-commuting gamma matrices. And here we reveal the concrete expressions for these matrices. Right. by revealing we split kind of this, we kind of split the symmetry. So we split it onto lorentz invariance. We split it onto time part, which we take simple, and we then the other matrices, three of them are presented as three-dimensional vector of spin, and this is really electron spin. So that's how Dirac equation can be written in more comprehensive coordinates, in more comprehensive notations, more physical notations. So here we have time derivative. X4 is related to time. And spatial derivatives come in combination with spin. Here we go. So eventually, as a byproduct of this operation, we got a notion of electron spin, which had been known by that time, didn't have a clear explanation yet. And now we can see that spin comes from relativity, in fact. But it is only one problem solved. More problems that came, right? First of all, this gammas are 4x4 matrices. It means that wave function should have 4 components. Well, if we have spin, we can live with 2 components, but it has 4. So here, these components are written as spinors, as 2-component vectors in 2 blocks. So that's called a B-spine. And there is kind of warning sign. This is a 4-component quantity. So first idea is to think it's a vector. It is not. It's called B-spiner. It's a separate representation of Lorentz group, special representation of Lorentz invariance. And actually, we will figure out soon which one, how Lorentz transformation transforms the wave functions. This gamma, it's also for component for quantity, but it's also not a vector. It's also conjugated by spinor. And what is a vector is a combination of this wave function and gammas. And that vector, as you will see later, is can be associated with 4-dimensional density of the current of the probability. Good. Dirac equation. To understand it better, no, we just solve it. Yeah. First, we want to get it in more in a form which we perhaps like more, in a form where we have only time derivative without matrices here. So look here, time derivative comes with matrix gamma 4. We want to get of it, so we just multiply it with gamma 4. This is what we obtain, and it has all properties of Schring equation. We have time derivative on the left-hand side, and that we find here, we can regard it as a Hamiltonian. By multiplication, the matrices have changed a bit. So this matrices alpha, which come with momentum or gradients, matrix beta. Fine. So let us go on solving that. Let's take the solution in terms of plane wave. There is important thing that one has to notice. All solutions of Dirac equations are solution of klein-gordon equation. So how we can prove it? This is operator which gives which corresponds to Dirac equation. We can multiply it with any other operator which is still valid. Let's multiply it with this operator. And as I showed earlier, just the Lambertian with a factor. But not every equation, not every solution of Dirac equation is a solution. Sorry, no other way around. Not every solution of klein-gordon equation is a solution of Dirac equation. Right, sure. Let us look for solutions in terms of plane waves. What does it mean? It means that we use this substitution, and that will give us algebraic equation for wave functions and energies, linear algebra. So we replace gradient by a number, which is momentum of a particle. Good. So this is equation to solve. This is a matrix. This is a wave function. So let us see how does it go. So there are two blocks in Dirac equation. We call it A and B. Right. First of all, to find energies. In order to find energies, in order to find the spectrum, one doesn't have to solve for wave functions. One could just take determinant of this matrix and see when it is zero. Well, that happens at this energy. So we have again this square root problem. Dirac construction does not remove that. We have solutions with positive and negative energies. Too bad. But anyway, let us proceed. Good. For positive energies, it's better to express with this equation psi b by psi a. For negative, it is better to express it in other way. Anyway, just application of this equation. And let us see what we have. That fixes psi A with respect to psi B or otherwise, but doesn't fix the original. So they can be chosen arbitrary. And we can recall the notion of spin. They should correspond to spin. So a choice which we can make that correspond to that projections of spin, and there are vectors like this. Good. If we are at rest for independent solutions of Dirac equation can be just written like this, like 4 ways to put zeros to put ones in these vectors. Right. One can also solve it for arbitrary momentum. The solution looks a bit cumbersome, but well, it's a straightforward solution. So again, this vector is either 0, 1 or otherwise for positive energies, or it can be 0, 1 or 1, 0 for negative energies. And there is again ugly square roots, ugly normalization vector. Good. We made it. We have solved the Dirac equation. And we understood that it has something to do with spin. Let us get some more order in these notations. Let's get some more feeling for that. With this, let us consider a convenient parameterization of first momentum and velocity. Let us see. We will introduce some whatever phase angle. Let's call it angle chi. It's a imaginary angle. And this automatically guarantees that energy and momentum are in the relation which we need. Next step is to deal with polarization. Well, we have a vector, which is a vector of momentum. So let us consider this as a quantization axis for spin. Good. So what does it mean? It means that the projection of spin on momentum is nothing but value of momentum, absolute value of momentum with two arbitrary signs. Right. Hey, look what we got after substitution. We've got 4 independent solutions for non-zero momentum now in terms of chi. Good, that looks kind of prettier than the original form. Let us see. Let us, oh, sorry, I should not have put it. But what did we do in fact? We just computed this solution for non-zero momentum, non-zero velocity. We could achieve the same if we just put ourselves in a moving frame. So in fact, this gives a Lorentz transformation for wave function of Dirac. How does it look like in a moving coordinate system? We see that this transformation eventually mixes up parts with positive and negative energies, so to say. And that also shows that it's not a vector, it is something distinct. It's a spanner that has different properties with respect to Lorentz transformation. Good. Then let us discuss very important conceptual breakthrough Dirac made. He was not only a mathematician, he was a man of genius also in physics. Good. What is the problem? The problem is negative energies. We can accept the spectrum. Fine. Electrons with positive energies. Energy at rest is mc squared, but we cannot really extract it. So we can forget it. We can regard it as a zero, for instance, electron from the rest. Doesn't matter. What is the problem with negative energies? The problem is that an electron, for instance, can emit a quantum and go to negative energy. Moreover, it can emit another quantum and get yet to more negative energy. It will accelerate and emit energy. So each electron under this circumstance would become an ultimate energy source, although the energy is conserved. It would just go to lower and lower energy. Sure, the first thought, of course, is the question is wrong, but the question is good. One cannot write again better equation without a concept of this negative energies. There has to be another solution, and that has been proposed by Dirac. And that solution is somehow rather trivial for us, but was highly non-trivial for that time. So what Dirac said is that electrons are fermions, and all these states with negative energy are field. That, of course, completely forbids any energy loss. So electron with positive energy would never be able to come to lower energy states because these states are fields. There is no place. And that kind of was, in fact, revolutionary by the time. It's a new concept of vacuum. It's full of particles, there are an infinite number of particles in this vacuum, and eventually it is full of charge. Right. The problem is that it is full of massive particles, which would create gravitational potential. I have discussed it with you. This problem have not solved yet. The same problem would be that our vacuum would be full of similar problem is that our vacuum, if only electrons are present, would be full of charge. Right. So it would mean that there would be a center of universe, an electric field, which would brought everything to the center of universe. It would be very strange and inconvenient world to live. But somehow we don't see this electric charge. And the solution is simple. I guess you know that. I can just figure out it in a second. So why infinite charge of electron vacuum is not a problem? Do I still have participants? Oh, I still do. Let's see. What time is it now? I'm not doing very well with this time. So I will answer this question itself, but it's really a question for us. It's simple, just requires some young imagination. The imagination would tell you that there are also positive particles which would have negative, which will have vacuum of negative particles at negative energy. And these two charges would compensate each other precisely. It would only suggest that electrons are not the only particles in the universe. There has to be particles with opposite charge and opposite energy. Right, so let us see. That was a solution of this paradox, solution of Dirac. And let us now make a good second quantization with this solution. So for each value of momentum, we will have 4 creation operators corresponding to the fact that wave function is 4 vector. Right, these operators are different spin, like electron operators, but they have also extra parameter, discrete parameter, whether they describe states with positive and negative energies. And what's a vacuum? It is made from a vacuum without the particles by filling all states with negative energy. Good. So let us now act on this vacuum with an annihilation operator. Annihilation operator of this minus energy states. And just for fun, I take it with opposite spin, opposite momentum. I have created an excitation. I have 1 electron less in the vacuum, so I have excitation with positive charge. And I have to switch pluses and minuses here, so it will have spin sigma, positive momentum, positive energy. Right. There are antiparticles, which are called positrons, electrons with opposite charge, particles which have the same mass, and electrons have opposite charge counterparts. So that was an origin of famous dichotomy of matter and antimatter. Right, and was purely theoretical prediction, which has been confirmed in, what's it like, 7 years after all. They really have discovered positron. I don't usually like, it's a kind of common Beziers concept to tell silly things about great people. But since you're a physicist, you must know that Dirac was a genius, but even if you're a genius, let's make it personal, you are not really, it's not guaranteed that you don't make silly mistakes. And after making this genius work, Dirac has made a silly mistake, namely he said that this antiparticle is in fact a proton. A proton has very distinct mass from electron. It could not be sure, so nobody still nobody can figure out why did he say so. But he did. Anyway, we are now in our business. We have established a new vacuum. We know operators of creation and annihilation. Let me talk a little bit about analogy with semiconductors. Of course, if semiconductors have been known in time of dirac, he wouldn't have to solve anything. They were not known. Right, so what we have in a typical semiconductor, we have a valence band for electrons. Sorry, we have conduction band for electrons. We have valence band for holes. Electrons in holes are excitations on the vacuum, on the background of vacuum. And right, usually in semiconductors, electrons and holes are not identical, coming from different bands. But well, in vacuum, they're precisely identical. So what matters is only the value of the gap. Well, most important difference is the symmetry, of course. The value of the gap doesn't matter. One can also think of analogies of massless particles in condensed matter, but for built in, for instance, in graphene, in a single sheet of graphite, one can have excitations which don't have any mass, which has a relativistic spectrum at Fermi energies, analogies of massless fermions. Good. So in the last minutes, I will tell you something about gauge invariance. We will recall this concept again. We will apply it to the dirac equation, and we will get, as we did before, interaction, thereby completing the build-up of relativistic quantum theory. These notes are rather trivial. Let me skip that. Gauge invariance. Let me remind what we've been talking about. A non-relativistic Schrödinger equation, which is like this. Remember, kinetic energy, potential energy, has a property of gauge invariance. Namely, one can transform wave function, assigning it a phase factor, and transform Hamiltonian accordingly, elongating the derivative. And one can transform current density, has to transform current density accordingly. And it will eventually give precisely the same physics. One can regard it as a mathematical property, but it is also gives you a way to introduce vector potential into Schrödinger equation. Instead of this gradient, one would just make Ron substitution, vector potential. Sorry, instead of gradient phi. It does have to be gradient, so it's not precisely the same equation, but it has the same structure. Let us talk about gauge invariance of Dirac equation. Let us do the same. Let's take relativistic form. Let's add a phase factor, which depends on coordinates and time. So there will be transform equation all derivatives are elongated with gradients, which will give precisely the same physics. Moreover, we have a bonus point in Schrodinger equation, since in Dirac equation. In Schrodinger equation, we have squares of derivatives, so we need to modify current density. For Dirac equation, we have only first order gradients, so we don't have to modify anything, and the current density conveniently remains the same on the gauge transform. But again, this transform is wide, just mathematical abstraction. If we would not associate this gauge field with electromagnetic field, right? What is a general prescription? What is general jump of logics which allows us to do this? The gradient which enters here is a general for vector, and the prescription is to regard it, to substitute it with a four-dimensional four vector of potentials, which, as we remember, contains vector part and scalar part. Good, that amounts to derivative elongation. And gives us Dirac equation in the presence of electromagnetic field. Good. Then we are now in business. We can have quantized, we have quantized electrons. We know how electromagnetic potential enters the equations for these electrons. And we know how vector potential is quantized. That we didn't do today, that we did several lectures earlier. And the reason for that is that photons are relativistic particles by nature. One doesn't have, their classical equations are relativistic by themselves. So now we can combine everything together. We have a Hamiltonian, which consists of electrons and photons and interaction between them. We can treat this interaction, for instance, by perturbation theory. This perturbation theory appears to be divergent. There's some care must be taken to make perturbation theory terms convergent. Small parameter which guarantees that perturbation theory should work is a fundamental constant. We talk about fundamental constant of alpha. It's must be the system. And right, with this you can build up relativistic quantum mechanics and explore the properties of physical vacuum. Many people have done so. If you would like to know about this, please consult proper literature. I just wanted to show that it's also a part of advanced quantum mechanics. One can proceed with the same methods. Ladies and gentlemen, that concludes my course. That concludes my lectures. It was a pleasure to work with you. to see of you present even in rather difficult circumstances. Well, in fact, they don't seem too difficult anymore. You get adjusted to them. I will be still here with you. There will be problem-solving sessions. There will be also meeting when we can ask questions about the course. There will be exam and proof exam, many activities. But my main business, the lectures are over. Sir, thank you for your attention. See you soon.